Hi guys, so I told you that I would only make this at most 25 minutes, so we'll see if I can go under 25 minutes. We left off today with talking about resonance, so I kind of want to go through and just review talking about resonance just a little bit more. I think that we talked about benzene, which is a very common organic molecule. You will more than likely see benzene on your AP Chemistry exam, or a question that corresponds with benzene. So you should know what benzene looks like, so you should know that this is a structure of benzene. You should know benzene is C6H6. So that means it has 6 carbons, and it forms more of a, it's called an aromatic structure, meaning that we have kind of more of a linked structure. So it has 6 carbons. So I have 1, 2, 3, 4, 5, 6 carbons here, and there's 6 hydrogens. So each carbon is going to have a hydrogen that's attached to it. Now I have single and double bonds that are alternating in benzene. So this one's a single, double, single, double, single, double. But that double bond doesn't have to necessarily be right here. It could have been right here. So benzene has resonance because maybe the double bond is here in this one, but it could be a single bond here. The double bond could shift over one. So that's why we have resonance there. Remember that resonance is where we can have multiple Lewis structures. It's just the placement of the double bond or the triple bond or the single bond is just going to be in a different place. So it's not that they're so completely different. It's just that it's the same thing, but the placement of the bonds are just probably opposite. They look almost like mirror images of one another in most cases. In terms of benzene, so a lot of times in organic chemistry, instead of writing it out this way, sometimes we write benzene out in this way, where each corner represents a carbon atom. So I have carbon here, 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 and here. So there's 6 carbons. And I know that there would be a hydrogen attached to each of those carbons. That's just kind of something that would be understood. So we know that hydrogens would be right there. And I know that I could have 3 double bonds in benzene. They could be here, 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 or I could shift them over one, and they could be here, here, or here. So these have a resonance with one another. We said yesterday that resonance, if I have 2 resonance structures, then it's like when we were talking about ozone, for example. I may have 2 resonance structures, but ultimately we're going to take kind of that synthesis of them to really get the true structure that we actually see in like everyday life. So we had ozone, for example, double bond here, single bond here, or I could have had the single bond here and the double bond here. And in that case, I really see in real life that instead of having the double and the single bond, I end up having the same bond length on both sides. The reason of that is because of something called the delocalized electrons. So when we have resonance structures, we have delocalized electrons. And we think about delocalized electrons when we talked about metallic bonding, because those electrons were delocalized, meaning that they weren't stuck or confined to one particular cation, or they weren't stuck or confined to one particular location. Instead, they're free to move around that molecule or to move around the other atoms that it's bonded with. So I have these 2 structures, but instead I can draw it like this, thinking about the double bonds or the electrons could be freely flowing anywhere around that benzene ring. The electrons are delocalized. So in resonance structures, we're going to have delocalized electrons. If we don't have resonance structures, then that means that we're going to have localized electrons. Those electrons stay put with those particular atoms. Okay, I want to get into exceptions to the octet rule. So there are 3 major types of exceptions here that don't follow the octet rule. And the first one that we'll look at is when we have an odd number of valence electrons. This should make total sense. If we don't have an even number, then I'm not going to have exact lone pairs. I may not get the number of single, double, triple bonds that I want. So if we have an odd number of valence electrons, of course you're going to have one little single electron off by himself, which that would be a definite exception to our octet rule. A second type of molecule or ion that doesn't follow the octet rule would be something that has less than an octet. So we'll see here, for example, that boron typically forms compounds that have molecules with less than an octet. And then our third type is ions or molecules that will hold more than 8 valence electrons, and we call that the expanded octet. Or we can also say that those are called hypervalent, meaning that they're going to have more than that 8. So let's go through and maybe look at examples of each one of these first. Okay, so if we have the first one, which was an odd number of electrons, this is incredibly rare. So this is very, very, very rare for this to happen. But we do have it happen. So if we have an odd number of valence electrons, then usually it means that that molecule or that ion is very unstable and it's pretty reactive. Usually we have ions, we have molecules with them. NO is an awesome example of an odd number of electrons. So if I think about NO and nitrogen monoxide, and I think about total number of valence electrons, we know nitrogen has 5, we know oxygen has 6, so the total number of valence electrons here would be 11. So I'm going to have a little odd electron that's out here. So I see that here, or that odd electron could be on nitrogen. I may see that odd electron on oxygen. So odd number of electrons, while they may be rare, they still occur. We still have them happen. Some other examples of an odd number of electrons would also be O2 minus. So O2 minus would be another example. ClO2 would be another example. And let's go to the next one. So the second case is where we have fewer than 8 electrons. In this case, let's take, for example, boron trifluoride. So we have B and then we have F around. I know that boron has how many valence electrons? Boron has 3, and then fluorine has 7, but I have 3 of them, so 21 electrons plus 3, that gives me, I need 24 electrons total. Well, if I look at this, I have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, so 12, 18, 19, 20, 21, 22, 23, 24. So this has all 24 of my valence electrons. I have all of those electrons counted for in this structure, but our rules have taught us that we want the central atom to have a complete octet. So we have thought, okay, if the central atom doesn't have a complete octet, then we should take one of those lone pairs from one of those outer atoms and see if we could double bond or triple bond or whatever we need to do here. So if we did that, I would get resonance structures, right, between all of these, because the double bond could be here, the double bond could be here, or the double bond could be here. So it wouldn't really matter in that case. If I do formal charge for all of these, if I do formal charge for this, and I do formal charge for this, I'm going to find that in every case, boron is going to end up having a negative charge if it has a double bond attached to it. And then one of the fluorines is going to be a positive 1. That should make absolutely no sense at all. Why would fluorine ever have a positive 1 charge? Fluorine is the most electronegative element that there is, so it would never want to have a positive 1 formal charge. So this is a terrible Lewis structure, which means this is a terrible Lewis structure, which means this is a terrible Lewis structure. If I did formal charge for these, I would find that all of them would give me a formal charge then of 0, which is exactly what I want. So because formal charge is 0 in this case, even though the central atom doesn't have that complete 8 electrons, it still has the best distribution of electrons around that central atom. So this would be my best structure, even though it doesn't have all of the 8 electrons around it. So that's why formal charge, when drawing these Lewis structures, is imperative. So let's have to make sure that we do those. So Okay, we pretty much already talked about this. It says, therefore, structures that put a double bond between boron and fluorine are much less important than the one that leaves boron with only 6 valence electrons. And that's because, in this case, we have all of these ending up with a formal charge of 0. So this is a very stable compound, versus these, which have one of the fluorines being a positive 1 charge. That's insane. It's just craziness. So the lesson that we want to take from this: if filling the octet of the central atom results in a negative charge on the central atom and a positive charge on the more electronegative outer atom, then we just don't want to fill the octet of the central atom. So if I can have something, even though my central atom may have fewer than 8 electrons, but I have formal charge to be 0 on everything, or I have formal charge to be 0 on the central and a negative for the most electronegative element, then that would be good. So that's our little lesson that we're going to take from this one. So the third type would be if we have more than 8 electrons. And I would just like to point out, I am at 11 minutes right now, so we're doing awesome. Okay. More than 8 electrons would be our third and last type. So the last, moving back to that second type, if we have less than 8 electrons around the central atom, that's also a very rare case. Very, very rare case. So the case that would probably be the most frequent, or maybe that we would see more often than not, would be more than 8 electrons around that central atom. And let's look for an example here, PCl5. So we have phosphorus and then we have fluorine here. We know that in this case, since phosphorus is going to bond to, I like how I have PCl5, but it should be PF5. Sorry about that, guys. In this case, if we're thinking about PCl5 or PF5, we know that phosphorus is going to be bonded 5 times. So that already is going to expand, or that's already past that octet. So it can do this. It just means that it's hypervalent. Typically, it is allowed to have an expansion of an octet, to have an expansion of the octet when we have elements on the 3rd row or below. We call those particular elements hypervalent. So usually those are the ones that we have like the d orbitals in that can participate in this. So it's very normal to have an expanded octet if we're thinking about atoms on the 3rd row or below. It just means that they're hypervalent. If we did formal charge on this, we would still find that it should be the most dominant structure. Okay, so again, thinking about our more than 8 electrons. Now, on our homework, and I think this was one on your homework too, and I know that some of you came in and asked me about this one too. And this is why I think it's really important that we do formal charge on all of them. We can't not do formal charge, because if we don't, then we may not get that right structure. So even though we can draw a Lewis structure for, this is phosphate ion, and we know our phosphate ion, we think we want it to have 8 electrons around that central atom, right? We want 8 electrons, we want that octet around phosphorus. So if I did that for phosphate, I know I have P here in the middle, because that would be my central atom least electronegative compared to oxygen. Oxygens all around. If I gave each one 3 lone pairs, then I find that I give them all of the valence electrons. So I have all of my electrons accounted for here. But if I did formal charge on this, I get this to be -1, this to be -1, -1, -1, but phosphorus has a +1 charge. We don't necessarily like that this central atom has a +1 charge. Is there a way that we could get phosphorus to have a formal charge of 0? Yes, you can. And that would be if we had a double bond to one of the oxygens. Then one of those oxygens would become a 0 formal charge. And then I'd have -1s on the most electronegative element or atoms in this one, which would be oxygen. It makes sense. This one is dominant because the central atom here is stable. So phosphorus would want to be hypervalent, meaning it wants to expand its octet. So this is the reason why formal charge is imperative. This isn't necessarily a wrong Lewis structure. It's just not the most dominant one. So from this point on, anytime you draw a Lewis structure, you have to write out those formal charges to make sure that you're right. Okay, so if we, like we said, we just double bonded this one here, then that eliminated that charge on phosphorus, it eliminated the charge on one of the oxygens. That makes it a more stable molecule, more stable compound. So this is the dominant one, this is the least or the less dominant one. So the lesson that we can take here, when the central atom is on the third row or below and expanding its octet, it can eliminate some formal charges. And if it can, you should do so. If any time we have any element third row or below and we can get a formal charge to be 0, that's what we want. We want that formal charge to be 0. It's meaning that it would bring about stability. Okay, so for practice, I would like you to just do, we'll do the third one in class together, but I would like you to do these two. So for class tomorrow, draw the Lewis structure of ICl4 with a -1 charge, and then draw the Lewis structure for XeF2. So do both of those for me for tomorrow, and we'll check them, we'll draw them on the board together and go through them. And then we'll also do this one together at the beginning of class. So the last thing that we need to talk about in chapter 8 is about bond enthalpies, or like bond strength. So very simply, the strength of a bond is measured by determining how much energy it's going to take to break that bond. How much energy is it going to take to break the bond? That is what bond enthalpy is. So bond enthalpy is just very simply the amount of energy that's required to break the bond. How much energy it is required to break the bond. That is bond enthalpy. So we have several of these calculated. We've done them experimentally. So of course, just like with our standard enthalpy of formations when we did that in the thermochemistry chapter, we had that in the thermochemistry chapter. You had that big reference table. We have the same similar scenario here in this case. So bond enthalpy for a chlorine bond is measured to be about 242 kilojoules per mole. What does that mean? That means I have to put in 242 kilojoules. This bond is going to have to absorb that amount of energy before it could ever break. Because remember, I have to put energy into breaking a bond. So when a bond is broken, remember that we have to absorb energy to actually break that bond. Remember, that was one of our misconceptions, that we think that when we break bonds, that means it has to release energy. But really, when we're breaking bonds, we have to be absorbing energy, because we have to have enough energy to break the bond. Okay, so if we're looking at this one, for example, we have methane CH4. So I have methane here, and if I think about this, all of these are the same, right? I have a CH bond here, I have a CH bond here, a CH bond here, and a CH bond here. So really it's like I have 4 of the exact same bonds. They're 4 equivalent bonds. Hopefully we all agree with that. If I want to find the bond enthalpy of methane, we have that calculated as 1,660 kilojoules. But that would be for breaking all 4 of those bonds. So how much would it be for breaking just one carbon-hydrogen bond in methane? Well, if I wanted to figure that out, I could just do 1,660 kilojoules divided by 4. And then if I did that, that would give me 415 kilojoules. So that means I would have to absorb, or this would have to absorb 415 kilojoules before that CH bond is broken. And that would be true for all of them. Okay, so hopefully that makes sense as well. And I want to go back really quick and just add a couple things. Let's just add a couple things here. Okay. Guys, so pretty much the stability of a molecule is related to the strength of its covalent bonds. The strength of the covalent bond between 2 atoms is determined by the energy required to break the bond. So let me go back and say that again. The strength of a covalent bond between 2 atoms is determined by the energy required to break the bond. So if I need more energy to break that bond, that means that that covalent bond would be stronger maybe than another one that we would be comparing it to. So, okay, let's keep going. So table 8.4 in your book will list some average bond enthalpies for many different types of bonds. So we have a CH bond, carbon-carbon bond, carbon-nitrogen bond. We can go through all of those, you can look at those, but we have those pretty much calculated already. So we have a table that we can look these numbers up. Average bond enthalpies are positive because when we are breaking bonds, it's an endothermic process. So when we're breaking bonds, remember that bond has to absorb energy. I have to add energy into that bond before it can break. So making bond or breaking bonds, bond breaking is an endothermic process. I have to put energy into that system if we think about it that way. Also, these are average bond enthalpies. So these are average. The reason that they're average is because sometimes that carbon-hydrogen bond could be, it may be in methane where all of them are the same, or it may be in something like chloroform where the chlorine may have that carbon and that hydrogen maybe interact a little bit differently. So these are just average bond enthalpies instead of just a straight, this is what we have. Guys, we're going to stop here and we will pick up here tomorrow at the beginning after we do our 2 practice ones and then the one that we'll do together in class. So you should be super proud. This is less than 25 minutes. Bye.